demodulator. We have a signal with a pulsation omega, which is known. And we have two parameters that are unknown, and one is interesting for us, is A, corresponding to the amplitude of the signal. So we measure Y, and in this exercise we want to find A. The first step is to find a state equation which generates the signal y of t. It will be our model, and from this model we'll be able to build a state observer so that we will be able to find the state and also the amplitude A and B also. So for this we'll take as a state variable x1 corresponding to omega y and x2 corresponding to the derivative of y. Okay, so the signal is like this, and in practice it corresponds to a modulated signal. So when we want to emit a signal, we have a carrier wave which is like this, high frequency with respect to time t, and we want to emit a signal like this, which contains some information. Okay, so this one is not a sign function, it can be any message, A of t. When we multiply the two of them, we'll obtain something like this. Whoop. So here we have the signal corresponding, so this envelope. From this envelope, if we are able to find the envelope, we'll be able to reconstruct A of t, and it is the role of the demodulator. So it is this signal that will be sent as a wave and will be received. So here it is the emitter, and it will be received in another place, and so the similar signal like this, assume that it will be exactly the same, and from this we'll want to reconstruct A of t, the amplitude. In this exercise we'll assume that A is constant, but in practice it moves slowly with respect to the carrier wave. Okay, so for the first question, we know that we have to find a state model for this. So we know that it is a sine function. So it can be modeled by a linear second order system. So normally we could take a state variable y and its derivative. But in this exercise we have chosen to take here to multiply by omega, which is known. So if y is a state variable, of course y omega is also a state variable. So from this we want a state model. So for this we have to write x.1, x.2, and here I am only allowed to have x1 and x2. There is no input. So for this I have to find x.1 equal. So x.1 corresponds to the derivative. Here it will correspond to y dot omega, but y dot is equal to x2, so it will be equal to omega x2. So this is why here I will write omega x2. Omega, of course, is constant. It's assumed to be known. This is why it is considered here as a parameter, and I am allowed to use it here. Now about x2. x2 corresponds to y dot dot, thanks to this. So it will be equal to y dot dot corresponds from this. I know that y dot dot is, so y dot is equal to a minus a sine omega t plus b, and I have to multiply by omega. And also y dot dot, so I have to differentiate y once more. I will have minus a omega square cos of omega t plus b. So this one corresponds to y of t, so it will be here equal to minus omega 2 y. So this and this corresponds to the differential equation which allows me to generate y. So here, since this one is equal to x1 divided by omega, thanks to this, then I will be allowed to write here minus omega x1. So here I will have x dot 2 equal, here it was this one, and here minus omega x1. Okay, so now I have my state equation here, which is linear. So I can rewrite in a linear form, in a matrix form. So in a matrix form, I will have x dot equal 0 omega minus omega 0 x, and y equal to, so I take this, 1 divided by omega 0 times x. So this is the state space model with no input. Here, no input. The output is y, and the corresponding y satisfy this model. So this one obeys this model. Now, what I will have to do is to build an observer here, which will reconstruct x hat, an estimation of x, and from this to be able to reconstruct an estimation y hat of this one. So this one will correspond to the filtered signal, and also I will be allowed to get a hat, an estimation of the amplitude. So this corresponds to the second question. So I assume that at time t I know the state vector x. We have to deduce an expression of the amplitude of the signal y in function of x of t. So we can understand from this model that if I have here x1, x2, then from this model I will obtain, due to this, trajectories which will turn like this around 0. So the initial equation, the initial vector is not known. I don't know on which circle I am, but I know that I will turn around 0 like this. And this will correspond to the A of t. Okay. So, second question. x1, I know it is equal to omega y, which is equal to a omega cos of omega t plus b. I know also that x2 equal to y dot, which is also equal to minus omega a omega sine of omega t plus b. So from this, I know that x1 square plus x2 square here and here is equal to a square omega square, and this square plus this square is equal to 1, so I get this. So I can conclude that a corresponds to 1 divided by omega times the norm of x. So it was what we have guessed here, except that this distance corresponds not exactly to a of t, but omega times a of t. Okay, so it was the second question where I have to prove this. So it means that from the norm of x, I am able to get the amplitude a. And now we can also understand that y corresponds to evaluate like this. Okay. Now, so we assume that we measure y and we have to find the state observer that would generate x hat. All poles will be placed in -1, and I will use a Luenberger observer. So so I'm here, and the observer I have to build is this one. Observer. So the Luenberger observer has the form x hat equal, so x dot what? A minus LC x hat plus Ly. Okay, where A corresponds to this matrix and C corresponds to this matrix. And L is unknown, so I have to find it, but I know it will have the form L1, L2. So 2 lines because x is of dimension 2, and 1 row because y is of dimension 1. So I know A and C, and the only unknown is L. All poles have to be equal to minus y. So it means that the constant time corresponds to 1 second. So recall that if I want a constant time of t, I have to choose a pole to something like 1 divided by t with a minus. The pole have to be negative, so that I am on the left part of the complex plane and I will be stable. So here I have no choice, I have to choose s minus 1. So it means that I will have to solve the determinant, so the characteristic polynomial of the evolution matrix of this. So it will be Si minus A plus LC, so the characteristic polynomial should be equal to S plus 1 square. So the pole will be equal to -1. Okay, so this one is equal to S square plus 2S plus 1. This one is equal to the determinant of, so here I will have Si, so Si is S minus y ys, so it corresponds to si minus a, plus lc, so plus L1, L2, so this one corresponds to L, multiplied by C, and C is 1 divided by omega, 0, as we have seen here. Okay. Now, this is equal to the determinant of S plus so L1 divided by omega due to this minus omega here S, this S, and here omega plus 1 divided by omega L2. Okay. If I compute this, I have to do that times this minus this times that, and I will obtain S squared plus 1 divided by omega L1S plus omega 2 plus L2. So now, since I want this polynomial equal to that polynomial, it means that this should be equal to 2 and that should be equal to 1. From this, I conclude that L1 is equal to 2 omega and L2 is equal to 1 minus omega squared. Or equivalently, we have the state, so the state observer is the following: x hat dot is equal to, so it's minus 2 omega minus 1 divided by omega 0, so this corresponds to A minus LC time x hat plus 2 omega 1 minus omega square multiplied by y. Here A hat is equal to 1 divided by omega multiplied by the norm of x hat. So it means that once I receive my signal y of t, I put this signal inside this observer, and this observer will give me y hat, but will also give me a hat, the amplitude I am interested with. So since I have x1, so this one corresponds to x hat 1, x hat 2, if I want to get the filtered signal, I will take this one. I will divide by 1 divided by omega, and I will get x hat. In the second part of the question, I have to build a program to check the behavior of the observer. So I will generate first a sampled signal with amplitude equal to 2, so which is unknown, and I will have to add some noise. So the noise will be white and Gaussian. I know the standard deviation, 0.1. And from this, I will implement the observer so that I will be able to compute the filtered signal y hat and the amplitude a hat. So I will consider the following Python program. This Python program uses the autolib library available here in Python. I will take as a sampling time 0.01, so dt, and I will compute up to 10 seconds. So recall that the constant time is 1 second, so 10 seconds should be enough. The amplitude is equal to 1, so the pulsation is equal to 1 radian per second, and the amplitude of the generated signal here is 2. So I add some noise, and the deviation is 0.1. So this one is white and Gaussian. So I run the program, and this is the signal I get, and all these points come from the noise. So I will have to estimate this the signal we can guess in the middle of this cloud of points. So here I have my signal y of t, which is generated with some random perturbation. Here the amplitude 2 to be found, and I will now program my observer. So the observer has different matrix. The first matrix is A, which is built here. So A, O like observer. B is this matrix. And here it is a C matrix because from X I am able, by multiplying by 1 divided by Y and 0, to get X hat. So here I have taken the first one in this block, but now I take the two of them. This is why I have such a matrix, which is called CO, or like observer, which is given here. Now I will integrate this differential equation, first order differential equation, by an Euler method here. So I will obtain x hat. X hat has been initialized here at 0, 0, because I have no idea of the amplitude. Then I generate x hat, so the estimation of the amplitude, like this, and y hat corresponds to the multiplication by the estimated state vector by the observation matrix CO. So what I will do, I will draw y red, so the signal that is entered as an input of my observer or my demodulator, because this block is also the demodulator. I will also draw here in black the estimated signal, which will be normally less noisy than the initial signal. And also I will draw the estimated amplitude in blue, A hat. I take my Python program here, I run it, and I will obtain here the perturbated y hat signal. The estimated, the initial in red is y of t. Here in black it is the filtered signal, which is less noisy, but at the beginning it is wrong due to the fact that I have a bad initialization. But after 1 second, after the constant time of 1 second, I obtain something which is quite accurate. And in blue it is amplitude. So amplitude is approximately equal to 2. So the estimation is quite good even with the noise. But at the beginning, due to the initialization, after I need to wait few seconds to have a good approximation, good estimation of the amplitude. Now the last question, I will try to draw the Bode diagram of the demodulator, and I will have to discuss, to give an interpretation of what I obtain. So the filter is made with this differential equation, with also this part, with the matrix A observer, B observer, C observer. So these matrices here are still here. So I will use the control toolbox of Python with a state space model, so from A0, B0, C0, and the direct matrix D0 equal to 0, since I have no direct matrix here. I will build the system called dem, like demodulator. So this system has an input y, and as an output y hat. This system is linear, and since it is linear, we can compute the transfer function, but I can also draw the Bode diagram. So I build it here, it is linear, and then here I build the Bode diagram. I put the option Hertz equal to false because I want to have in radian per second. Okay, so recall that omega is equal to 1, so we may expect that the frequencies or the pulsation around 1 radian per second can cross this filter quite easily. I switch to Python. Here I run this program. So here it is again with respect to the pulsation omega, and here it is the phase change. So around omega equal to 1, here I have a gain which is almost equal to 1, so which is equal to 1, and here the gain is almost 0 because we have a logarithmic scale. Also here around omega equal 1 I have no phase change, which is a frequency analogy and consistent with what we expected for our demodulator.